Hello everyone. Today we are going to finally get out of the Introduction to Radioactivity section of this unit. And today we're going to focus on one particular aspect of nuclear chemistry called transmutation. You can see the word here. So my aim is, what is transmutation? There will be a classwork that you'll need to do, but we should have time to do that in class. It's 16 through 23 on page 221. So please copy that assignment down at the end of the classwork things that you're going to need to copy down. So yeah, 2 pieces of paper. One of them is for Cornell notes, but you also need to have a second piece of paper that goes in the classwork section of your binder with the date. And it should have the do now copied down, and then it should have the pair up copied down, and the summary. All of those 3 things copied down, and then finalize it with this heading for this homework, and we'll work on it in class. Okay, I'm going to start the lecture now. So the aim is, what is transmutation? Pause the video right now and make sure you have this do now copied down. I'm going to glance around the room when you come in to see if you have it ready. Okay, so mini lesson. As we've already said, radioactivity is when a nucleus breaks down into smaller parts. There are some vocab words like decay and emit that you can use that are really helpful here. Decay means to fall apart, and emit means to give off. So basically, the nucleus itself is made of particles, and forces inside the nucleus make it split open and spit out all of its particles. Now, this can be a natural process, but there are times when it's not a natural process. It's artificial. And when it's artificial, it's happening by force. There is an easy way to tell when this is happening by force, when the decay is forceful. And an example right here of a natural decay will get us started in identifying artificial as well. So this is considered natural decay right here. All right, so here's my explanation of the reason why this kind of decay is considered natural. Natural means it happens by itself. It means that it's not been done artificially. And it's really easy to tell that this particular decay is natural because this isotope of polonium-168 is transforming into bismuth-168. And I can tell it's happening naturally or by itself because there's no other nuclide on the left-hand side of the equation with polonium. Polonium's by itself. So that means it must be decaying naturally. So it's decaying because it's turning from polonium to bismuth, and it's decaying naturally because polonium is by itself on the left-hand side. So here's my vocabulary word. As we're changing from polonium to bismuth, the element is transforming. And any kind of transformation, when you go from one element to another element, that's always called transmutation. So I'm going to circle it a few times in red because that's your vocabulary word. Transmutation is the process of changing one element into a different element. All right, so what has changed about polonium to transform it into bismuth? You should pause the video and think about all the ways polonium changed as it became bismuth. So here's what I came up with. Firstly, as polonium changes into bismuth, I can see that the atomic number decreases by 1. I can see that the mass has stayed the same. It went from 168 to 168, so I'm going to leave that out. But I will say that a positron has been emitted. And if you're checking your math, and you always should, you should make sure that all the mass numbers on the top of the equation add up to be equal on the 2 sides, and all the charges on the bottom of the equation add up to be equal on 2 sides. So we have 168 on the left, and 168 plus 0 is 168 on the right. On the left we have 84, and 83 plus 1 is 84, so 84 is equal to 84. So natural transmutation is basically what we just went over. This is called natural decay. It's also, in this case, natural transmutation, as it goes from polonium to bismuth. But just to focus on natural transmutation a bit more, natural transmutation is when the nucleus decays and turns into a different element all by itself, hence the word natural. So under what circumstance will natural transmutation occur? That's when the nucleus is unstable because of some problem with the neutron to proton ratio. So there is another kind of transmutation, and that is artificial transmutation. Artificial just means that it's not happening by itself, therefore it's not natural. I think you should think of it as the opposite of natural transmutation. But in artificial transmutation, you'll still have the element turn into another element, but it'll do so because it was forced to do so. It was made to do so, and that's why we would use the word artificial. There is a practical side to this. You need to be able to tell when you're looking at an equation if it's artificial or if it's natural. As you learned, you can tell if it's natural if the particle is alone on the left-hand side of the nucleus and transforms by itself on the right. But if you see an extra particle on the left-hand side, we use this word right here. It says bombard. We call that a bombarding particle. And you can think of it as a particle that has been thrown at the nucleus and is, through a collision, it's forcing it to break open. Sort of like a piñata would break open when you hit it with a bat. So just like when you break open a piñata and like all the candy spills out, if you break open a nucleus, you're going to get a huge number of particles spilling out, and some of them will be sort of like accidental particles, but others of them will be the nucleus in its new identity as it's lost some protons, maybe gained some neutrons, and it will have transmutated. So here's an example. In this particular example, I'm showing you a nuclide of aluminum, and this guy right here, I'll circle it in red, this alpha particle or this helium nucleus, in any case, it's a bombarding particle because it is shown on the left-hand side of the equation, and it's clearly colliding with the nucleus of aluminum. So this guy's bombarding the aluminum nucleus, and when it does so, it causes the aluminum to transmutate into phosphorus-30 in this case. There's an extra little bit that's coming out of the nucleus as well, and it's a neutron in this case. But this guy, the identity of this guy, this extra bit, that could really be anything as long as the algebra works out. And this could really be anything as long as the algebra works out. But just keep in mind that if you want to identify this as artificial transmutation, that in addition to the nuclide on the left-hand side, you must have a bombarding particle as well. All right, so moving on, we know that this nuclear reaction is artificial because there is a bombarding particle on the left-hand side. And going further, so here's another question. It says, would you have a better chance of breaking open the piñata of the nucleus if you were throwing rocks at it, whether it was a small child or a pro wrestler, and why? So pause the video and think about an answer. So my answer is that the pro wrestler would probably have an easier time breaking open the nucleus with bombarding particles because he can throw with more energy. So in physics, we actually have a pro wrestler who can throw these particles at the nuclei, and it's called a particle accelerator. There are plenty all over the world. The most famous one is at the CERN Institute in Switzerland, but it basically is a giant underground magnet, and you can think of it as a racetrack of sorts, only the cars are bombarding particles, and instead of using gasoline to move themselves, we use magnets inside the particle accelerator to make the cars move. So we basically just spin those bombarding particles at really high speeds using magnets, and they slam into a nucleus that we're aiming it at, and in rare cases, it'll break the nucleus open and we're able to study what comes out. One interesting thing is that really there are only a few particles that you can use inside a particle accelerator. One of those particles is an alpha particle. Protons would work as well. And the thing that alpha particles and protons have in common that make them easy, I would say, culprits for use in a particle accelerator is that they both have mass and they both have charge. So the magnets that power the particle accelerator would have no effect on, let's say, a neutron or a gamma ray. And although those otherwise might be good particles to throw, if they don't have charge, they cannot be accelerated using the magnets. So the particle accelerator is really only going to work on alphas and protons because they have mass and charge. So I included that just now, and I also went ahead and wrote in that neutrons cannot be thrown in particle accelerators because they are not charged. But when a nucleus splits, and that could be artificial or natural, when a nucleus does split open, some neutrons will spill out, and those flying neutrons have the ability to rip open neighboring nuclei quite easily. The advantage that neutrons have that makes it really easy for them to split open nuclei is that they have mass, but they don't have charge. And that lack of charge means that they can't be used in a particle accelerator, but if they are flying around anyway because of artificial or natural transmutation, then those neutrons are easy. It's easy for them to penetrate the nucleus since they have no charge and the nucleus would not be able to repel them. Okay, so that basically concludes the lesson. Remember to have a separate piece of paper that you copy down the do now. You copy down the pair up, which I'm going to show you in a moment, and that you copy down this summary as well. So pause the video and copy down the summary. Don't, on that separate paper, don't answer it yet. Okay, and on second thought, I'm looking at this pair up, and I'm realizing that it is 16 through 23. And if you go back to the beginning of the lesson, 16 to 23, I think, was your homework that you had to do. So you do not, you're off scot-free this time. You don't need to copy down this pair up, but we will be answering these questions, all of them. They'll be straight from the book, and we'll do it in class. So do not copy these down. You can just preview them if you want, but don't copy them down and don't solve them yet.